It's just part of their shooting and kind of the things. That's what it's like some of that. So that's what we make next. Yeah. I'm like facing this part of the car. Even if I was bad, only 80 that's 90%. It's not something that is so the fucking it's still look at. But it's yes, I think it's 50 years old. Yeah, it's fancy. I don't know if I want to deal with it. Everybody knows your post. Especially now. Now, basically, it's not that. But then that was a big yeah. I was talking about so it's working out in the back end. And then the other side, follow down, going down. First. So once you start going, you start spinning. So I
Should be good whenever you're ready.
thanks. But then you going like sideways. They go sideways. And so it finally gets something going, takes itself back. So it's just like. There's no blood that you're not supposed to. No, yeah. Yes. Hello, Monty. We have one more optional homework remaining.
The content of homework 11 is not optional, only the homework submission is optional. Be aware of that. I've said this before, there are two questions, if you look into the last papers, that always come from the same format, that it involves a ray diagram, and usually the last two questions. So that's should be an easy question to prepare for. That pretty much takes care of a big chunk of the concepts that we covered in the last two homeworks. So that's a advice for the study. Any questions in general? Notice that the due date is not a usual one. It is usually we have it right before a lecture. This is on the last hour of Friday. I cannot make anything due beyond Friday officially, but this has a room there, so almost you have about 24 hours of buffer there, so feel free to submit even afterwards. Anything else I should be mentioning here? Okay. Let's cover the topics that we need for working on homework 11. We have been dealing with ray optics. Ray optics involves light. We constrain ourselves to wavelengths between 400 and 700 nanometer. That's pretty much, I think, very roughly to have a feel for how much it is. It is the size of a bacteria. Those are the things that we can see. And we make a big approximation that we say that it is no more a wave. Instead, a wave is approximated by a straight line. And we want to talk about refraction today. Light, as we have understood, is an electric or electromagnetic phenomenon. It doesn't require charges or currents, unlike what we have studied before, that electric field is generated using charges and magnetic field is generated using currents. But light is a very special phenomenon where electric field can create magnetic field and magnetic field can create electric field, and in itself they together can sustain each other without any charges or currents involved, and that requires oscillations of electric and magnetic field, and that's represented by this. These are perpendicular to each other. Okay, so that's how it looks like. If you have electric field in one direction, magnetic field is perpendicular to the electric field, and that's direction of propagation. But we said we are not interested in, or at least at the first step we do is that we do not want to deal with the complete description. A complete description will be necessary if you're doing more precise, let's call it communication. Radar communication is an example where you have to take care of the wave nature of the electromagnetic wave involved. But there is a very special approximation. If the wavelength lambda, and wavelength is the periodicity in space, if wavelength lambda is very much large compared to the irregularities on the interface, so this is irregularities. So smoothness is an inverse of if there are less number of irregularities, that means it is very smooth. So this means this is related to smoothness. So if a surface is very smooth, it can be an interface involving a mirror, a glass, two mediums anywhere. If the wavelength is significantly larger compared to irregularities, or in very simple terms, if the surface is very smooth, then we don't have to worry about these details, and we can just talk about a ray. So that's a ray. But that comes with the price that this doesn't have too many properties, right? If you have a straight line, what does it depend on? It seems like it does not depend on anything. It just depends on the direction of propagator. That is a straight line, that is a direction associated with it, but it doesn't even seem to have a magnitude associated with it. But no, that's what I want to highlight today. Here we will talk about a property of a ray, which is the speed of the ray. So the speed of the ray will be the speed of light in the medium. So in that sense, when I say that there is a ray, there is a direction associated with it. We already used that feature earlier. Any straight line has a direction, but now we associate a magnitude also to it. So it has a direction and a magnitude, and this magnitude is related to the velocity or the speed of light in the medium. So we will, so K is here 2 pi over lambda. But lambda now is not the wavelength of light in vacuum. We will say it's the wavelength of light in the medium. So there is only one property in the ray optic approximation, that's the direction, the speed of light in the medium. So let's talk about how does things change if you have a one parameter which is the speed. So let's define what is called a refractive index. Of a medium. Refractive index will be denoted by the letter N. So that's refractive index of a medium. As I said, it is going to be described using a property which is speed of light in that medium, and that will be equal to C, which is the speed of light in vacuum, divided by speed of light in the medium. So this is speed of light in vacuum, and that's speed of light in the medium we are interested. What will be the dimension of refractive index? Anyone? What will be the dimension of refractive index? Nothing, because the ratio speed of light, speed both cancel out, and then it has no dimension. It is a pure number that we have. What can it? How much can it be? Notice that speed of light in vacuum is the fastest speed you can attain to our understanding as of today. Nothing can go faster than speed of light in vacuum. That doesn't mean that you cannot go faster than speed of light in a medium. In fact, you can go exactly like fighter planes can go faster than speed of sound in air. And whenever that happens, you have a shock wave. Similarly, light in a medium goes slower than speed of light in vacuum. So something else can take up that space in between and something else can go faster. So there are particles which can go faster than speed of light in the medium, but not speed of light in vacuum. And the effect associated is called Cherenkov radiation. We won't be discussing that, that is just for your general knowledge. Here, what we are interested in is that every medium you can think of, we will talk about water, glass, air, diamond if you want, and metals. So this is broadly the materials that we will be working with. So let me list them. So this is medium, and this is the refractive index N. Vacuum is the easiest. Vacuum has speed of light in vacuum is C itself. C over C is 1. So that's 1. So that's a perfect one in the sense that it is to all significant digits, it is 1. So that's the number 1 if you want the integer number 1. If you have air, that's very closely related or closely a vacuum, and to 2 significant digits, it is exactly 1.0. So speed of light doesn't change much when it is traveling in air. But how much does it take? If you were to make more precise measurements, which has been done, you can go 3 and about 4 significant digits. I think that is a 5 there. Something like that. So as far as you're working in 2 or 3 significant digits, there is no difference in vacuum and air within our accuracy. The next field you can think of is water. That's about 1.3 to 2 significant digits. Glass is 1.5. It depends on which glass we are talking about. Different properties, different materials that build glass leads to a small change in the second digit, but very broadly it is 1.5. That is diamond, which is slightly larger, it is 2.5, and that's because of the structure of diamond. But what's relevant is that how high can you go? It is metal has a very high refractive index usually, and this, let us for our purposes, let's say it is infinite. So practically speaking, in principle, it can actually be very slow, and there have been experiments where speed of light has been reduced significantly inside a material, and this is very simplistic. It is not necessarily the simple metals that do the job, but I'm just talking about a hierarchy there where you can go from 1 and all the way to increase. But to have materials beyond 2 is very hard. 2.5 is diamond. But beyond that, it is definition of refractive index itself changes. It's a frequency dependent quantity, and the definitions itself take a more tedious definitions, let me call it. Okay, so that's the property that we want to deal with. Again, notice it's a speed of light in a medium we are talking about. We use a parameter called the refractive index, but the property of the physical essence of that is the same. Let's talk about a very closely related phenomena, but let's talk about walking. Speed associated with walking, or let us say you're driving on an interstate and certain roads are faster than some other roads, and that's what we want to have the refractive index into picture. The speed can change from one medium to the other. So let's have a let's call this Fermat's principle. Fermat's principle was stated for light, but here I'm going to discuss that, at least at the beginning. I'm going to discuss this for a normal person walking. in a, let's say, so this is a rectangular shaped platform where you can walk, and it is divided into two regions. And this is, let's say, concrete, and that's sand. And the basic difference being that it is much easier to walk on concrete than on sand. So if there was a race you had to perform, you will be able to do much better on concrete than on sand. So our basic idea is the velocity on concrete is significantly larger for a normal person than on sand. So you have velocity v1 here that you can walk with, and this is v2. Associated with that is a definition called refractive index. In this case, we won't call it refractive index because we don't have a speed of light. We're talking about humans, but we are going to, the idea will be built on this, but immediately we'll talk about light because all the relations we use does not capture whether it is a human or a light that is traveling. Our goal will be to start from one corner and reach the other corner in the fastest possible time. So, or shortest time possible. Yeah, you don't say fastest, right? Shortest time you have to reach from one end to the other. If there was no interface here at all, there was a single medium, it doesn't matter whether it was V1 or V2, you would have gone in the straight line. That would have been the shortest path. We all know that if you want to go from one corner to the other corner of the room, if everything is uniform, then you go in a straight line. But now you know that this is faster. Imagine two roads. One is faster, but it takes a longer route. The distance traveled is longer, but then very quickly you realize that, oh, there is something optimal between them. One road takes longer. The distance traveled is longer. On the other one, the velocity is larger. So together there might be a compromise between them. So that's what we wanted to do, and we expect that if since this is faster, you would like to spend more time there. You don't want to spend all the time there. For example, you don't want to go all the way here and then reach, because then the distance traveled is too long. So somewhere there is a compromise. And that's what we want to figure out. So, and that's your x, we want to call it. So here, this distance. So that's your x. So that's 0. That's your x. And the total distance should be d. 0xd. And we are interested in finding out how much should the value of x be, so that the time taken to go from one corner to the other corner is a minimum. So t is equal to t1 plus t2. You want to minimize this time t, and we know that time t1 taken is given in terms of velocity. So that's distance over velocity, right? So we need to have distance. So that's d1, and let's say that's d2. All these are parameters we are introducing, but very quickly we'll bring it down to a relation which will be very useful. So that's distance d1 over velocity v1 plus distance d2 over velocity v2. And we would like to minimize that. So our equation reads t as a function of x. We don't want to write it in terms of d1 and d2. We want to find the particular value of x for which this time is a minimum. So I want to replace all the distances with the value of x. So distance d1 is equal to d1 will be, that's x, and I said both these are the same heights, so let's say this is x and that's h. So too many parameters being introduced, but all this will go away, and we will talk in terms of a single parameter, but allow me to introduce all this. So distance d1 is there is a right triangle here, that's x, that's height h. So I have x squared plus h squared over velocity v1 plus, if that's x, that's d minus x, and the same property, distance d2 is plus height h squared over velocity v2. That's an equation for the time taken to go from one corner to the other corner in terms of this parameter x, which is a variable. In the sense, I have not really told at exactly what value of x we would really like to go. If you want to minimize this, we know that the slope of this function has to be 0. That's what we learned in calculus. If you have a function and you want to minimize that value, you take the derivative and set that to 0. So we would like to do partial derivative, or there's only one parameter. Oops, sorry. There's only one parameter, so it is dt over dx has to be set to 0. So find the derivative, set it to 0, so it's any function, presuming that there is a minimum. At the minimum value, the slope is 0. Slope is the derivative of the function, so dt by dx has to be set to 0. So I need to take the derivative on the right side also. Derivative of a square root brings the square root in the denominator, because 1 by 2 minus 1 is a minus 1 by 2. So it brings the the whole square root in the denominator, and then you take the derivative with respect to the argument of the square root. So this will be 1 by 2, that's the power of square root, and then 1 by 2 minus 1 practically brings this down. So that's x squared plus x squared. And take the derivative of the argument, which is 2 times x. 1 over v1 just sits there as expected. So that's the derivative of the first term. The same thing happens in here, except that there is a minus sign in there. So there is 1 over 2, 2 times d minus x. And the derivative involves this minus sign, so this changes to minus 1. That minus sign contributes to the derivative as a minus sign there. And the whole thing, it is d minus x squared plus x squared. And again, v2 is just sitting there doing nothing. That's your equation. If I want to set this to 0, this has to be equal to this because that's a negative sign. So that's a relation I have. So let me cancel out the factors 2. And then is this quantity x over x squared plus x squared that is showing up. X is this distance here. And x squared plus x squared is the distance d1. The distance over the hypotenuse for a right triangle is the sine of this angle. So a new parameter now, theta 1. But I promise that will be the last parameter, and that's what will be the parameter we'll work with. X over distance, d1 is the square root of x squared plus x squared. That's nothing but sine of theta 1. So what this implies is that sine of theta 1, that's this quantity, divided by v1 is equal because it's negative, I can put it on the other side. And the other ratio is d minus x, that's d minus x over distance dq, that's sine theta 2 over v2, where sine theta 2 now is again with respect to the normal, and that's theta 2. Now change the whole scenario. Let's not talk about someone walking from concrete to sand. Instead, this is glass, or this could be air, and this is glass. Glass is denser, so the speed is smaller. So we said sand on sand, the speed is smaller. So this could be glass, that could be another medium, and we say that now we want to write it in terms of refractive index. So I multiply by C on both sides and identify C over V1 as the refractive index and 1. This will be a governing equation at the interface between two mediums, and this is called the Snell's law. Of refraction. Earlier, we have talked about an interface. So this is a mirror. And we talked about what happens to light when it comes and hits this interface. We said that the angle of incidence is equal to angle of reflection. Right? That was the property that governed it right at the interface. Now we are talking about the same similar interface, but now the light can go into the second medium. The medium is described by the refractive index. For very simplistic understanding, the density of the medium practically decides how fast light can go, but more importantly, it is the electrical property of the material that matters. So remember that as we go down, metal has can get slower, so it is the electric and magnetic properties that decide what the refractive index is, but nevertheless, it is how properly you can crystallize the material that does decide. So for example, diamond has a very high refractive index, and that's because you can really condense the diamond as a solid material as a crystal. So for our purposes, we will now investigate what does this mean. Where again, simplistically speaking, sine theta is monotonic in the small angle approximation. So sine theta is oscillatory, but for small angles, it increases. That's sine theta. As angle theta increases, sine theta increases in that small value. So if you think of this as just an angle, if n1 times theta 1 has to be the same as n2 times theta 2, if you decrease the refractive index, the angle has to increase. So angle and the refractive index, the product of that has to be conserved, has to be the same on the left and the right. If you increase the refractive index, that means you're going from air to water, the angle has to decrease. If refractive increases, the angle has to be decreasing. So that's a basic simple idea that we'll be using. And let us do the geometry when light is now going across an interface. Earlier we talked about light reflecting off an interface, and now we are talking about light going through an interface, and we will come across a very interesting phenomena in the sense that sine of an angle cannot be greater than 1. So that puts a restriction on this equation. Not all values of angle are actually possible. Like there are certain angles for which sine of that particular angle can be beyond 1, and that leads to very, very interesting, very non-trivial applications. And a very simple application which we use all the time is a fiber optic cable, which is used for internet communication. In fact, 99.9% of internet communication happens through fiber optic cables, and that uses this principle, not in this straightforward form, in fact, in a non-trivial form, for it talks about regions where sin theta is not really equal to 1, and then what happens. So let's investigate that. So let's now go back to law of refraction. Let's start with Snell's law. Let's talk about refraction now. There are two distinct configurations you can think of. One is when light goes from a rarer medium to a denser medium. A rarer means we will have the terminology rarer and denser. What this means is that, of course, it has to be relative to something. So rarer means that we're talking about something that is denser, and one, in this case, n is small, right? Compared to something denser, here n is small, larger or larger. Like that's broadly what we will say. We will use the terminology that light goes from a rarer medium to a denser medium. Example could be air. That's air, and this could be glass. It could be glass, or it could be water. When you go from water to glass, then water is related to glass. It is always, when you say denser, it is related to something, and you need two properties to talk about. Let's have an interface here. So this is air, and that is it could be water. That could be a fish inside water, and let's say light is going from here and going into the water. So the observer, so this is the source, or we can say this is the object. And then we say source, which is basically a source of light, but you don't need a source of light. You can always have light coming and falling on the material, and then it behaves like a source. For example, moon is not really a source of light, but it reflects the light from the sun. For all practical purposes, moon does have light, a source of light. In that sense, this is a source. Light will be coming in and reflecting off that, and then for that moment we are talking about a source. Somewhere here there is an observer. That's your eye. That's your observer. And we want to see how does that look like to an observer inside water. So you think of a fish, how a fish perceives things outside when it is looking out into the or from water, it is looking outside into land objects. How does it look like? So remember, any eye, our brain is designed, our brain, and presumably fish's brain also is designed so that it takes two rays of light, it extrapolates it backward, and wherever they meet, that's where the object or that's where the image is. So we have one ray of light starting this way, and now we have to decide what does it do when it goes into the medium. We draw a abstract line, that's your normal line, that's normal line perpendicular to that, and all of these angles that we talk in ray optics is with reference to the normal line. Let's say that's angle θ1. And by L, we mean this is N1, that's N2. One for this to two significant digits, it's 1.0, and N2 is 1.3. Let's say angle theta 1 is 30 degree for our purposes, and now we have to talk about what happens to the angle theta 1 once it enters. Notice N1 times N1 goes from 1 to 1.3, it has increased. That means if you want to keep Snell's law intact, and 2 times sine theta 2, the product of these two quantities for analysis purposes, you can just think of it as a linear angle. N1 has increased, so angle theta 2 has to go down. And 1 increases from 1 to 1.3, so the angle decreases. So it has to decrease into the medium, so it doesn't go straight here. It would have gone straight, but instead the angle decreases, so it bends towards the normal. So that's angle theta 2. So ray bends, towards the normal. So that's a statement of refraction, that whenever light goes from a rarer medium to a denser medium, the ray bends towards the normal. Basically, the angle is decreasing because the refractive index has increased. But where does the observer, what is the effect of this associated to the observer? For an observer, you need two rays of light. So this is only a single ray of light. So you can either take a second one very close to that. And since the angle now is slightly larger, this one also will be slightly larger, but nevertheless, this will be like this. It will make a cone slightly larger, remember, and if you were to project this backward, that's where this will be. That means to say, anything that is standing next to the surface of water, for fishes down in the water, they look much bigger because it has bent, and when you project it backward, it is significantly larger. So for objects in air look significantly larger for fishes that are viewing it from denser medium into the rarer medium. Remember, light is going from rarer to the denser medium. It is just that the observer is inside. So this is the image. That's your object. That's your image. One can ask, is that image a virtual image or is it a real image? Notice there is no light actually going there. It is just a projection extrapolation. So there is no real image formed there, and just a virtual image. It is a projection of the eye. We imagine it to be, it's an illusion if you want, that we think there is an image there. If the light were really to converge there, at that point, then you say it's a real image. Here, if you were to keep your hand there, it is not going to get, you won't feel any warmth due to the light that is going in there. In fact, you could keep a flat metal sheet there, an opaque object, and still you will feel that there is an image there. So it's a true illusion in that sense. So for eyes or observers inside a dense medium, things coming from the rare medium look bigger with reference to the height, if you want. What happens if you do the opposite? Let's now pretend that you are outside, so the observer is outside and the source is inside the water. A very classic example would be that there is a small coin that has fallen into the swimming pool, and you feel, oh, that's, so that gives you a depth of the swimming pool. Or the swimming pool floor, what is the judgment you make about the depth of the pool standing on the edge of the pool itself? So we do the same analysis again, but this time, light is below, so that's N2 is 1 point, or let's say this is N1 now, correct? But N1 is 1.0 and N2 is 1.3. It doesn't really matter what you call N1 and N2, but I'm saying one is being, the idea is that it is the first of the source is being represented by one, but there is no such rule for it. Let's say it starts from water, so that's like a coin, and that's acting like source, which is the object. The light comes and falls on a coin that is lying on the bottom of the swimming pool, and from there it reflects out. So it's acting like a source, or if you really want to make it a source, make an electric bulb there inside the pool. So you have designed it so that it is because it can still function inside, and there is a source of light in there, and there is a ray of light that goes in and goes to the interface. Right? That's your ray of light, and again you draw a normal line, and that's your angle θ1 this time. When the light is going from, oh, I said it wrong, right? Thank you. So this is 3, and I meant water swimming pool air, right? Sorry about the confusion. You're talking about a small coin, so this could be a coin on the floor, of a pool of water. So as a floor swimming pool, it could have been 2 meters deep. There is a coin there, light falls on it, and it acts like a source, and it tries to go out, and at the interface, the refractive index is decreasing, but the product of the refractive index and the angle has to remain the same. So if this decreases, the angle has to increase. So the angle cannot go straight. It would have liked to go straight, like the concrete and the sand example. Everything would have gone straight if the speed of light or speed did not matter at all. But here, if you go straight, then they are going to take more time. You want to, light pretends to take the shortest path, so it's a bigger angle. It bends away from the normal. It bends away from the normal. So that's a few significant configurations you can have. In one case, when it goes from rarer to denser, the light bends towards the normal, and when it bends, when it goes from denser to a rarer medium, the light bends away from the normal. So how does this affect how we interpret things? So that's your eye. This is now humans looking at aquatic organisms, let's say, and or this is just a coin, right? For our purposes, we are just going to project this backward. Straight line. So straight line, you just project it backward, and that is somewhere here. But I need 2 rays of light to really know where it is going to intersect. The easiest typically is to go straight. And when you go where with an angle 0, then there is no deviation at all, and you immediately know where it is going to intersect. But it is always good to think of an eye because it gets only a small cone. So for that purpose, let's have that's as another ray, second ray, going very close to itself. and it deviates a little more. Then, and it forms a cone, and if you do everything correctly, precisely, if you project it backward, it will come exactly here so that it will meet exactly at a vertical point above the coin. So the coin will be displaced upward, which means that the depth of the pool. So for our perception, we interpret the depth of the pool by how far the coin is. That's our interpretation. That's our inability to be able to, or it's often an ability in the sense that it is useful for us in other contexts. But here it becomes how do you say that? It is not a positive factor in the sense we make a wrong interpretation that the swimming pool apparent depth is smaller than the actual depth. And how much is it? We can actually tell that this is angle theta 1. If that's theta 2, that's angle theta 2. And if I were to draw this again, so we have a triangle like this. Oh, this is roughly what is, or this is precisely what is happening here. If that's angle theta 1, this is angle theta 1, that's theta 1. And if that's angle theta 2, that is angle theta 2. So that's theta 2. We are interested in the depths. So this is the apparent depth. Let's call it prime. Like what we interpret, that's not the actual one. And that's your actual depth. So that's your height or actual depth of the swimming pool. We would like to know the ratio of h prime over h. And it tells us that, oh, that is a triangle that you can make out of it. So let's say this is height h. Oh, sorry, I don't want to call it h because I've already used that. So like x. So we have from the property of the triangles, you have x over h prime is equal to tangent theta 2 and x over h is equal to tangent of theta 1. Both are the same x's, so h times tangent theta 1 is the same as h times h prime times tangent theta 2. So h times tangent theta 1 is equal to h prime times tangent theta 2. If your angles are small, if they are not large enough, that means to say that you're looking at it from almost the coin is at the edge, very close to the edge, the angles that you form is very small. In that case, tangent theta is the same as sine theta. So that's sine theta 1 approximately is equal to h prime sine theta 2. For small angles, let's say small angles. You can try this in a calculator. You should investigate that if you do sine of a 10 degree and a tangent of a 10 degrees, how much off it is. It is a good exercise to do so that you have an idea of how much close these quantities are. We have sine theta 1 and sine theta 2 related by refractive indices, so we can replace that sine theta 1 by sine theta 2. Where was our Snell's law? Sine theta 1 is, if you write a ratio sine theta 1 by sine theta 2, so you get n2 over n1. So what we have is h over h prime is equal to sine theta 2, so that's n1 over n2. So h prime then is equal to h times n2 over n1. Let's do this for water. N2 over N1 is 1.0 divided by 1.3. And that's equal to that's about 0.77 times height. If the height was 1 meter, it's only 3/4 of that height. So this diagram is not very true representation of it. So this will be about so much. Right? So that's still it is a significant, it's 25% of it. So that's significant that you you could make a significant error in there. That's two very one can say reasonably straightforward conclusions you can make out of Snell's law. But as I said, there is a non-trivial conclusion that comes out of this, because sine of an angle, or for that matter, sine or cosine of an angle, cannot take values beyond 1. And how does that show up here? So let's think of those equations. This is broadly called total internal reflection. And there are a lot of non-trivial optical phenomena you can explain using this. For our purposes, when you look at an application, since the optical fiber that we use for internet communication is using this idea. So what is this based on? It is again just Snell's law. Again, let's start with a dense medium. Let's this time take glass. N is equal to 1.5. Let's say N1 is equal to N1.5 and N2 is air. That's 1.0. It's going from glass to air. And remember, optical fiber is plastic, but the material has very close properties to a glass. It could be somewhere about 1.45 up to the refractive index. We already argued that if light were to go from glass to air, we have, let's say if this is angle theta, it actually bends away from the normal. So that's how it would like to go, but it bends away. If that is the case, so that's theta 1 and that's theta 2. That's a representative ray diagram for a particular ray. And now have the simple idea that you want to increase your angle theta 1. So slowly increase your angle theta 1. The second ray could be this, right? So that's another ray which has a larger theta 1. That means to say it has to compensate for the larger refractive index. So the angle of refraction will be significantly larger. So let me label them. That's ray 1. After refraction, it reaches here, and ray 2 reaches here. Keep increasing. Notice that this is smaller, theta 1 is smaller than theta 2. That is a very critical angle, that is a very particular angle for which the angle of refraction is exactly 90 degrees. Right, so that's, let me say, critical angle. So that's C, and that's C. The ray is C, and this particular angle we will call it the critical angle. That should raise a lot of questions as to what will happen if there was a ray from here. So that ray source of light can go in any direction you want to, and if there was a source here and it were to reach here, where does it go? What it means is that there is no refraction happening. That light cannot penetrate into the other surface. It will only reflect. Reflection always happens at any interface. So beyond a certain angle, there is no refraction possible when you're going from a denser to a rarer medium. There can only be reflection. And what that means is that you're not losing any energy outside, which is very useful when you're doing communication. For communication, the main point is that we do not want the signal to be lost. You want as much as possible, you want to keep going in a particular direction. And this is the feature you use. So you want to use or exploit this feature, but we'll come to that. But let's first ask, what is the critical angle for when light is going from glass to air for total internal reflection to happen? So that's straightforward. You would say N1 sin theta 1 for any of these rays is equal to N2 sin theta 2. That's the general Snell's law. But for the critical angle, what happens is N1 times critical angle now is equal to N2 times, for the critical angle, the angle of refraction is exactly 90 degrees. So that's sine of 90 degrees. Sine of 90 is 1. So we can calculate the critical angle. So that's N2 is 1 divided by 1.5. And the critical angle is 2/3. So it's sine inverse. And that's 42 degrees to 260 degrees. Notice that's not a very large angle. So anything beyond 42 degrees cannot go from glass to air. In other words, if you were to design it properly, so remember that this point is no special, right? This point is also a possible way for materials to go up or light to go out. But if you were to design something such that this is opaque, then if you were to stand here, you won't be visible from outside. Like if you had a feature where this was filled with water and light could not go from here, so this is opaque. And if you stand here, you will not be visible from outside because light from here cannot get out. So there are places inside a medium where you can hide as far as optics is concerned. There are other ways you can detect it, but if you're standing here using straightforward optics, light cannot touch this because all of that will only get reflected and not get refracted. So that's a cloaking mechanism, a trivial cloaking mechanism, if you want. This is the critical angle. I said this is used for in fiber optic cable. So how do we do this? So we would like to have, so let's say this is a cable, and fiber optic cable has this additional feature that you can actually, this is very flexible. This is made up of plastic, so it's not brittle like glass. So it has this added feature that you can bend it around. That played an important role because cables you would like to bend go around places, but we're not worrying about that. So we just say this is a straight cylindrical wire. At the interface, let's approximate, or let's think of it as a cross section. So that's a rectangular cross section when you're looking at from one end. This is air, and that's glass. light has to enter. Let's say that's your reference light. Light enters from here, and that's your angle theta. And after it enters, this is again add. So somewhere light is entering. So first, what you do is that all the electrical signals or any communication that you're making, you convert it into light. So you code all the information electrical signal into light signal, and that light signal is going in. It is going from air into glass, and it bends. Right? It would have liked to go straight, but it doesn't go straight. It bends. And if that bend, as far as your input signal is within a certain angle, which we will calculate just now, if you are within a certain cone angle, such that this is exactly theta c. If this is theta c, that's your maximum. If you're any angle beyond this angle theta, if you're within this angle theta, you are only increasing your theta c, which means that you won't go up. Right? A small decrease in angle theta will change this to only larger. That means it cannot go up. And if this was satisfying this condition here of total internal reflection, then this goes in here. If that's angle theta c, this will again be angle theta c. So once you're met it at one surface, you're good. It will never, remember, there is absolutely no energy going out. You're not losing any energy because there is no energy being lost as refraction. It's only getting reflected. Reflected means it is going forward. That's exactly what we want. Right? So it keeps reflecting off, it won't lose any energy. Having said that, there is one small place where it does lose. This is just to make the statement correct, that there is some amount of energy that is lost on the surface. So you can always ask, where does this energy go? It is not that everything gets reflected. Most of the refraction energy, a good bit, goes on the surface. They are called surface waves, or they're called evanescent waves, but we will not talk about that here. It is relatively small, but nevertheless, there is a loss. So we do need to put in repeaters. So every certain amount of distance, you have to amplify that signal again and send it through again. But nevertheless, this is a very convenient way of a situation where you exploit the fact that light energy is not lost in refraction. Let's calculate what should this cone angle be. Like if you want to send the signal through a cable, what should angle theta be in terms of theta c? Again, it comes out of geometry. That is all there is to it. So that is angle theta, theta c, and we need to do a geometry out of it. So let me do that. So that's your triangle. So that's theta c, and this will be theta 2 if you want. Theta prime, let's call it. So that's the refracted, and that's your angle theta. And you also have, this is n equal to 1.0, and that's n equal to 1.5. Let's pretend it is glass. Larger it is, better it is, then the angle is smaller. And let's do geometry of this. We have n1, so it's 1.0 sine theta is equal to 1.5 times sine theta prime. But sine theta prime is nothing but 90 minus theta c. So that's 1.5 times cosine of theta c. Sine of theta prime will be cosine of the critical angle in there. We would like to replace this in terms of refractive index. So let's write this as 1.5 times 1 minus sine square of theta c, and sine square of theta C is nothing but N2 over N1, right, where N2 was the air, so it is 1 over 1.5. So it is 1.5 divided by 1 minus 1.0 square over 1.5 square. So the cone angle that you have to send the signal into is given by, take this in, that's 1.5 square minus 1. So in general, if this was refractive index was n, this is actually n squared minus 1. So that's a very simple equation coming out of geometry. But again, having said this, the basic initial idea remains. But the challenge usually is that the refractive index is frequency dependent, in the sense that by frequency we mean color dependent. If you're using light, red light and blue light have different refractive index, and you have to take care of those phenomena. They travel at different speeds too. So due to that reason, you have to make sure that after a certain distance, they do not have any phase lag between them. So there are challenges associated with that. It doesn't come out trivial as it is shown, but the basic idea remains the same. From there, you build on this fact. There is another very nice phenomenon you can explain using total internal reflection. And that's called the mirage. And here first we will talk about the inferior mirage. That is a very corresponding phenomenon that is called the superior mirage. Inferior mirage happens in hot places. On a hot summer day, the interface of road serves that purpose. So this is an inferior mirage, and what the idea is that you have, let's say, a hot surface. So this is a hot summer road serves as a good example, but typically the classic example is desert. If you have a desert, then the sand is very hot on the surface on a hot day, and hot air is lighter. Hot air is lighter means that the refractive index is smaller for hot air. So this is hot air and this is cold. That means refractive index increasing. So large refractive index and a small refractive index here. And let us, so this is very simplistically speaking, we have layers of gold. And let's have a tree. So that's a tree. Simplistic. So that is a palm tree. Let's say it's a desert. That's a palm tree with only 2 leaves on it. And there is light that falls on it. So that's your object. And light goes in a straight line, but it can go in a straight line only in one small segment of the medium. This happens continuously. But for simplicity, we are making this into finite segments. The refractive index is larger on the higher surface. So when it goes to the lower surface, it bends away from the normal. So it bends away from the normal. Instead of going down here, it has bent away from the normal. Next one, again bent further. And after a while, it cannot bend any further because then it's total internal reflection it has to do. So it cannot refract anymore. So it starts going up. So it has got reflected there, and now it reverses the whole step. And this actually happens continuously instead of going straight. So each point there is a refraction happening. This is an observer. This could be you standing in here. And when you're traveling on a desert, you're desperately looking for shade or for water, and there is one ray, you project it backward, you can have two rays, and when you project it backwards, what you see is you see a reflection of this of the tree. That's your image. And hot surface has a feature that there is fluctuations in the air. So this is not just an image, that is a simmering image because it is fluctuating. And our eyes interpret any fluctuations as a liquid, and we think that there is water in it. So this is a reflection of a tree. And you will often see this on a hot day on an interstate when you're driving. When you look on the road very far away, you feel that there is water on the road. But then as we get closer, that's getting farther and farther. That's exactly this. But that is what is called a superior mirage, which is much more dramatic. This is already dramatic, but then you get used to it because you see all the time. A superior mirage is on a cold day when the ground is really cold, make it opposite. So this is cold, and that's hot. And now the refractive index is in this direction, and now your eyes. So light now goes this way. So let's say in this direction, and we again project it backwards. You will see it here. So if there were typically what happens is that on an ocean, on a very cold day, there will be a boat on the ocean, and you will see the boat floating in air. So that's an illusion that forms due to exactly the opposite form, because again you're projecting it backward. Light is bending instead of going this way, light is going to make it go like this, and you project it in a straight line, and everything will look floating away from the ground. So that's called a superior mirage. Look it up. There are nice videos of these phenomena that you can check around these days. Thank you. We'll talk about spherical interfaces next time.